Learning objectives. In this chapter, the user will learn the following in detail. Breadth first search BFS, depth first search DFS, branch and bound, topological sort, strongly connected components, Euler tour, generic minimum spanning tree, Bellman-Ford algorithm, matching, incremental design, closest pair problem. Bellman-Ford algorithm. The Bellman-Ford algorithm solves the single-source shortest path problem in the general case in which edge weights may be negative. Given a weighted directed graph G equals V, E with source S and weight function W, E implies R. The Bellman-Ford algorithm returns a Boolean value indicating whether or not there is a negative weight cycle that is reachable from the source. If there is such a cycle, the algorithm indicates that no solution exists. If there is no such cycle, the algorithm produces the shortest path and their weights. The algorithm relaxes edges, progressively decreasing an estimate V dot D on the weight of a shortest path from the source S to each vertex V belongs to capital V, until it achieves the actual shortest path weight delta of S, V. The algorithm returns true if and only if the graph contains no negative weight cycles that are reachable from the source. In this example, the execution of the Bellman-Ford algorithm on a graph with 5 vertices. The source is vertex S. The D values appear within the vertices and shaded edges indicate predecessor values. If edge of U, V is shaded, then V dot pi equals U. In this particular example, each pass relaxes the edges in the order T, X, T, Y, T, Z, X, T, Y, X, Y, Z, Z, X, Z, S, S, T and S, Y. The situation just before the first pass over the edges. The figure B2E, the situation after each successive pass over the edges. The D and pi values in part E are the final values. The Bellman-Ford algorithm returns true in this example. Lemma. Let G equals V, E be a weighted directed graph with source S and weight function W, E implies R, real valued weights on the edges. And assume that G contains no negative weight cycles that are reachable from S. Then, after the mod V minus 1 iterations of the for loop of lines 2 to 4 of Bellman-Ford, we have V dot D equals delta of S, V for all vertices V that are reachable from S. Proof. We prove the lemma by appealing to the path relaxation property. Consider any vertex V that is reachable from S and let P equals V0 up to Vk, where V0 equals S and Vk equals V. Be any shortest path from S to V. Because shortest paths are simple, P has at most mod V minus 1 edges, and so K less than or equal to mod V minus 1. Each of the mod V minus 1 iterations of the for loop of lines 2 to 4 relaxes all mod E edges. Among the edges relaxed in the ith iteration for I equals 1 up to K is Vi minus 1, Vi. By the path relaxation property, therefore, V dot D equals Vk dot D is equals delta of S, Vk equals delta of S, V. Corollary. Let G equals V, E be a weighted directed graph with source vertex S and weight function W. E implies R, real valued weights on the edges, and assume that G contains no negative weight cycles that are reachable from S. Then for each vertex, V belongs to capital V, there is a path from S to V. If and only if Bellman-Ford terminates with V dot D less than infinity when it is run on G. Theorem. Correctness of the Bellman-Ford algorithm. Let Bellman-Ford be run on a weighted directed graph G equals V, E with source S and weight function W. E implies are real valued weights on the edges. If G contains no negative weight cycles that are reachable from S, then the algorithm returns true. We have V dot D equals delta of S, V for all vertices V belongs to capital V. And the predecessor subgraph G pi is a shortest path tree rooted at S. If G does contain a negative weight cycle reachable from S, then the algorithm returns false. Proof. Suppose that graph G contains no negative weight cycles that are reachable from the source S. We first prove the claim that at termination, delta of S, V for all vertices V belongs to capital V. If vertex V is reachable from S, then the above lemma proves this claim. If V is not reachable from S, then the claim follows from the no path property. Thus, the claim is proven. The predecessor subgraph property, along with the claim, implies that G pi is the shortest path tree. Now we use the claim to show that Bellman-Ford returns true. At termination, we have for all edges U, V belongs to capital E. V dot D equals delta of S, V, which is less than or equals delta of S, U plus W of U, V is equals U dot D plus W of U, V. And so, none of the tests in line 6 causes Bellman-Ford to return false, therefore it returns true. Now suppose that graph G contains a negative weight cycle that is reachable from the source S. Let this cycle be C equals V0 to Vk, where V0 equals Vk. Then, summation of I equals 1 to k, W of Vi minus 1, Vi less than 0. Assume for the purpose of contradiction that the Bellman-Ford algorithm returns true. Thus, Vi dot D less than or equals Vi minus 1 dot D plus W of Vi minus 1, Vi for I equals 1 up to k. Summing the inequalities around cycle C given as shown in this figure. Since V0 equals Vk, each vertex in C appears exactly once in each of the summations. Summation of I equals 1 to k Vi dot D and summation of I equals 1 to k Vi minus 1 dot D. And so summation of I 1 to k Vi dot D equals summation of I equals 1 to k Vi minus 1 dot D. Moreover, from the above corollary, Vi dot D is finite for I equals 1 up to k. Thus, 0 less than or equals summation of I equals 1 to k W of Vi minus 1, Vi, which contradicts inequality. Conclude that the Bellman-Ford algorithm returns true if graph G contains no negative weight cycles reachable from the source and false otherwise. Branch and bound. Branch and bound is a technique for exploring an implicit directed graph. This graph is usually acyclic or even a tree. This time, looking for the optimal solution to some problem. At each node we calculate a bound on the possible value of any solutions that might happen to be farther on in the graph. If the bound shows that any such solution must necessarily be worse than the best solution found so far, then we do not need to go on exploring this part of the graph. In simplest version, calculation of these bounds is kind with a breadth first or a depth first search and serves only to prune certain branches of a tree or to close certain paths in a graph. More often, however, the calculated bound is used not only to close off certain paths but also to choose which of the open paths looks the most promising so that it can be explored first. Depth first search finishes exploring nodes in inverse order of their creation, using a stack to hold those nodes that have been generated but not yet explored fully. Breadth first search finishes exploring nodes in the order of their creation using this time a queue to hold those that have been generated but not yet explored. Branch and bound uses auxiliary computations to decide at each instant which node should be explored next, and a priority list to hold those nodes that have been generated but not yet explored. Example: traveling salesperson problem used to illustrate this technique. Let G be the complete graph on 5 points with the following distance matrix. Looking for the shortest tool, starting from node 1 that passes exactly once through each other node before finally returning to node 1. This node in the implicit graph correspond to partially specified paths. For instance, node 1, 4 and 3 corresponds to 2 complete tours, 1, 4, 3, 2, 5 and 1, and 1, 4, 3, 5, 2 and 1. The successors of a given node correspond to paths in which one additional node has been specified. At each node, we calculate a lower bound on the length of the corresponding complete tours. To calculate this bound, suppose that half the distance between 2 points I and j is counted at the moment we leave I and the other half when we arrive at j. For instance, leaving node 1 costs us at least 2, namely the lowest of the values 14 by 2, 4 by 2, 10 by 2 and 20 by 2. Similarly, visiting node 2 costs us at least 6, at least 5 by 2 when we arrive and at least 7 by 2 when we leave. Returning to node 1 costs at least 2, the minimum of 14 by 2, 4 by 2, 11 by 2 and 18 by 2. To obtain a bound on the length of a path, it suffices to add elements of this kind. For instance, a complete tour must include a departure from node 1, a visit to each of the nodes 2, 3, 4 and 5, not necessarily in this order, and a return to 1. Its length is therefore at least 2 plus 6 plus 4 plus 3 plus 3 plus 2 equals 20. Notice that this calculation does not imply the existence of a solution that costs only 20. The root of the tree specifies that the starting point for our tour is node 1. Obviously, this arbitrary choice of a starting point does not alter the length of the shortest tour. Just calculated the lower bound shown for this node. Our search begins by generating, for a breadth first search, the 4 possible successors of the root, namely nodes 1, 2, 1, 3, 1, 4 and 1, 5. The bound for node 1, 2, for example, is calculated as follows. A 2 that begins with 1, 2 must include the trip 1 to 2, 14, formally leaving 1 for 2 and arriving at 2 from 1, 7 plus 7. A departure from 2 toward 3, 4 or 5, minimum 7 by 2. A visit to 3 that neither comes from 1 nor leaves for 2, minimum 11 by 2. A similar visit to 4, minimum 3. A similar visit to 5, minimum 3. A return to 1 from 3, 4 or 5, minimum 2. The length of such a tour is therefore at least 31. The other bounds are calculated similarly. Next, the most promising node seems to be 1, 3, whose bound is 24. The 3 children 1, 3, 2, 1, 3, 4 and 1, 3, 5 of this node are therefore generated. To give just one example, calculate the bound for node 1, 3, 2 as follows. The trip 1 to 3, 3 to 2 is 9. A departure from 2 towards 4 or 5, minimum 7 by 2. A visit to 4 that comes from neither 1 nor 3 and that leaves for neither 2 nor 3, minimum 3. A similar visit to 5 is minimum 3. A return to 1 from 4 or 5, minimum 11 by 2, which gives a total length of at least 24. The most promising node is now 1, 3 and 2. Its 2 children 1, 3, 2, 4 and 1, 3, 2, 5 are generated. This time as node 1, 3, 2, 4 for instance corresponds to exactly one complete tour 1, 3, 2, 4, 5 and 1. Do not need to calculate a lower bound since we may calculate immediately its length 37. Find that the length of the two 1, 3, 2, 5, 4 and 1 is 31. If we are only concerned to find one optimal solution, do not need to continue exploration of the nodes 1, 2, 1, 5 and 1, 3, 5, which cannot possibly lead to a better solution. Even exploration of the node 1, 3, 4 is pointless. Why? There remains only node 1, 4 to explore. The only child to offer interesting possibilities is 1, 4 and 5. After looking at the two complete 2s, 1, 4, 5, 2, 3 and 1 and 1, 4, 5, 3, 2, 1, find that the two 1, 4, 5, 2, 3, 1 of length 30 is optimal. This example illustrates the fact that although at one point 1, 3 was the most promising node, the optimal solution does not come from the. To obtain answer, looked at merely 15 of the 41 nodes that are present in a complete tree of the type illustrated in the figure of branch and bound. The need to keep a list of nodes that have been generated but not yet completely explored, situated in all the levels of the tree and preferably sorted in order of the corresponding bounds, makes branch and bound quite hard to program. The heap is an ideal data structure for holding this list. It is next to impossible to give any idea of how well the technique will perform on a given problem using a given bound. There is always a compromise to be made concerning the quality of the bound to be calculated. With a better bound, look at less nodes, but on the other hand, most likely spend more time at each node calculating the corresponding bound. In the worst case, it may turn out that even an excellent bound does not allow us to cut any branches off the tree and all the extra work I've done is wasted. In practice, however, for problems of the size encountered in applications, it almost always pays to invest the necessary time in calculating the best possible bound within reason. For instance, one finds applications such as integer programming handled by branch and bound, the bound at each node being obtained by solving a related problem in linear programming with continuous variables. Breadth first search. Graph introduction. Graph is a data structure that consists of a set of nodes and a set of edges that relate the nodes to each other. Formally, a graph G is defined as follows. G equals V, E, where V of G is a set of vertices, E of G is a set of edges. Vertex. A node in a graph is called vertex. Edge, arc. A pair of vertices representing a connection between two nodes in a graph. Undirected graph. A graph in which the edges have no direction. Directed graph or digraph. A graph in which each edge is directed from one vertex to another or the same vertex. Example is shown here. Weighted graphs. Each edge of the graph has an associated weight. Example of weighted graph is shown here. Graph algorithms presents methods for representing a graph and for searching a graph. Graph representation. Two standard ways to represent a graph G equals V, E. Adjacency list, adjacency matrices. Either way applies to both directed and undirected graphs. Adjacency list. The adjacency list representation provides a compact way to represent sparse graphs. Example for adjacency list representation of directed graph is shown here. Adjacency matrix. Prefer an adjacency matrix representation when the graph is dense or when we need to tell quickly if there is an edge connecting two given vertices. Example for adjacency matrix representation of undirected graph is shown here. Graph searching. Searching a graph means systematically following the edges of the graph or visit the vertices of the graph. A graph searching algorithm can discover the structure of a graph. Many algorithms begin by searching their input graph to obtain this structural information. Several other graph algorithms elaborate on basic graph searching. Breadth First Search (BFS). Breadth First Search is one of the simplest algorithms for searching a graph and the archetype for many important graph algorithms. For example, Prime's minimum spanning tree algorithm and Dijkstra's single source shortest paths algorithm use ideas similar to those in breadth first search. Given a graph G equals V, E and source vertex S, breadth first search systematically explores the edges of G to discover every vertex that is reachable from S. It computes the distance smallest number of edges from S to each reachable vertex. It also produces a breadth first tree with root S that contains all reachable vertices. For any vertex V reachable from S, the simple path in the breadth first tree from S to V corresponds to a shortest path from S to V in G. That is, a path containing the smallest number of edges. The algorithm works on both directed and undirected graphs. Breadth first search is so named because it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. That is, the algorithm discovers all vertices at distance k from S before discovering any vertices at distance k plus 1. To keep track of progress, breadth first search colors each vertex blue, green or black. All vertices start out blue and may later become green and then black. A vertex is discovered the first time it is encountered during the search, at which time it becomes non-white. Green and black vertices, therefore, have been discovered, but breadth first search distinguishes between them to ensure that the search proceeds in a breadth first manner. If U, V belongs to capital E and vertex U is black, then vertex V is either green or black. That is, all vertices adjacent to black vertices have been discovered. Green vertices may have some adjacent blue vertices, which means the frontier between discovered and undiscovered vertices. Breadth first search constructs a breadth first tree, initially containing only its root, which is the source vertex S. Whenever the search discovers a blue vertex V in the course of scanning the adjacency list of an already discovered vertex U, the vertex V and the edge U, V are added to the tree. That U is the predecessor or parent of V in the breadth first tree. Since a vertex is discovered at most once, it has at most one parent. Ancestor and descendant relationship in BFS defined relative to the root S. If U is on the simple path in the tree from the root S to vertex V, then U is an ancestor of V and V is a descendant of U. Example is shown here. In this figure, node A is an ancestor of both B and F, and B and F are descendants of node A. The breadth first search procedure BFS, which is shown in this figure, assumes that the input graph G equals V, E is represented using adjacency list. It attaches several additional attributes to each vertex in the graph. Store the color of each vertex U belongs to V in the attribute U.color and the predecessor of U in the attribute U.py. If vertex U has no predecessor, for example, if U equals S or U has not been discovered, then U.py equals nil. The attribute U.d holds the distance from the source S to vertex U computed by the algorithm. The algorithm also uses the first in, first out Q, capital Q, to manage the set of green vertices. Although We won't use this loop invariant to prove correctness. It is easy to see that it holds prior to the first iteration and that each iteration of the loop maintains the invariant. Prior to the first iteration, the only green vertex and the only vertex in Q is the source vertex S. Line 11 determines the green vertex U at the head of the Q and removes it from Q. The for loop of lines 12 to 17 considers each vertex V in the adjacency list of U. If V is blue, then it has not yet been discovered and the procedure discovers it by executing lines 14 to 17. The procedure paints vertex V green, sets its distance V dot D to U dot D plus 1, records U as its parent V dot pi and places it at the tail of the Q. Once the procedure has examined all the vertices on U's adjacency list, it blackens U in line 18. The loop invariant is maintained because whenever a vertex is painted green in line 14, it is also enqueued in line 17 and whenever a vertex is dequeued in line 11. It is also painted black in line 18. The results of breadth first search may depend upon the order in which the neighbors of a given vertex are visited in line 12. The breadth first tree may vary, but the distances D computed by the algorithm will not. Analysis. Before providing various properties of breadth first search, take on somewhat easier job of analyzing its running time on an input graph G equals V, E. After initialization, breadth first search never apply blue in a vertex, and thus the test in line 13 ensures that each vertex is enqueued at most once, and hence dequeued at most once. The operations of enqueuing and dequeuing takes big O of 1 time, and so the total time devoted to queue operations is big O of V. Because the procedure scans the adjacency list of each vertex only when the vertex is dequeued. It scans each adjacency list is at most once. Since the sum of the lengths of all the adjacency lists is big theta of E, the total time spent in scanning adjacency lists is big O of E. The overhead for initialization is big O of V, and thus the total running time of the BFS procedure is big O of V plus E. Breadth first search runs in time linear in the size of the adjacency list representation of G. This figure illustrates the progress of BFS on a sample undirected graph which shows the operation of BFS. Q contains S. Here the Q contains W and R. In this figure, the Q contains R, T, X. In this figure, the Q contains T, X, V. In this figure, the Q contains X, V, U. In this figure, the Q contains V, U, Y. In this figure, the Q has U, Y. In this figure, the Q has Y. Finally, the Q has nil. Tree edges are shown selected as they are produced by BFS. The value of U dot D appears within each vertex U. The Q is shown at the beginning of each iteration of the while loop of lines 10 to 18, which is shown in this figure of BFS procedure. Vertex distance appear below vertices in the Q. Shortest paths. At the beginning of this selection, claimed that breadth first search finds the distance to each reachable vertex in a graph G has V, E from a given source vertex S belongs to V. Define the shortest path distance delta of S, V from S to V as the minimum number of edges in any path from vertex S to vertex V. If there is no path from S to V, then delta of S, V equals infinity. Call a path of length delta of S, V from S to V a shortest path from S to V. Before showing that breadth first search correctly computes shortest path distances, we investigate an important property of shortest path distances. Closest pair problem. It is also called as closest points problem. The input to our first problem is a list P of points in a plane. If P1 equals x1, y1 and P2 equals x2, y2, then the Euclidean distance between P1 and P2 is x1 minus x2 the whole square plus y1 minus y2 the whole square, the whole power 1 by 2. We are required to find the closest pair of points. It is possible that two points have the same position. In that case, that pair is the closest with the distance 0. If there are n points, then there are n of n minus 1 by 2 pairs of distances. We can check all of these obtaining a very short program, but at the expense of an big O of n square algorithm. Since this approach is just an exhaustive search, we should expect to do better. Let us assume that the points have been sorted by x coordinate. At worst, this adds big O of n log n to the final time bound. Since we will show an big O of n log n bound for the entire algorithm, this sort is essentially free from a complexity standpoint. The following figure shows a small sample point set P. Since the points are sorted by x coordinate, we can draw an imaginary vertical line that partitions the point set into two halves, PL and PR. This figure shows a small point set. Either the closest points are both in PL or they are both in PR, or one is in PL and the other is in PR. Let us call these distances DL, DR and DC. The following figure shows the partition of the point set and these three distances. This figure shows P partitioned into PL and PR. Shortest distances are shown here. We can compute DL and DR recursively. The problem then is to compute DC. Since we would like an big O of n log n solution, we must be able to compute DC with only big O of n additional work. We have already seen that if a procedure consists of two half-sized recursive calls and big O of n additional work, then the total time will be big O of n log n. Let delta equals min of DL, dr. The first observation is that we only need to compute DC if DC improves on delta. If DC is such a distance, then the 2 points that define DC must be within delta of the dividing line. We will refer to this area as a strip. As shown in the following figure, this observation limits the number of points that need to be considered. In our case, delta equals dr. This figure shows two land strips containing all points considered for DC strip. There are two strategies that can be tried to compute DC. For large point sets that are uniformly distributed, the number of points that are expected to be in the strip is very small. Indeed, it is easy to argue that only big O of square root of n points are in the strip on average. Thus, we would perform a brute force calculation on these points in big O of n time. The pseudocode in the following figure implements this strategy, assuming the C++ convention that the points are indexed starting at 0. In this figure, the brute force calculation of min, delta, DC is shown. In the worst case, all the points would be in the strip, so this strategy does not always work in linear time. We can improve this algorithm with the following observation. The y-coordinates of the 2 points that define DC can differ by at most delta. Otherwise, DC greater than delta. Suppose that the points in the strip are sorted by their y-coordinates. Therefore, if Pi and Pi's y-coordinates differ by more than delta, then we can proceed to Pi plus 1. This simple modification is implemented in the following figure. This extra test has a significant effect on the running time because for each pi, only a few points pj are examined before pi's and pj's y coordinates differ by more than delta and force an exit from the inner for loop. The following figure shows, for instance, that for point P3, only the 2 points P4 and P5 lie in the strip within delta vertical distance. In the worst case, for any point Pi, at most 7 points Pj are considered. This is because these points must lie either in the delta by delta square in the left half of the strip or in the delta by delta square in the right half of the strip. On the other hand, all the points in each delta by delta square are separated by at least delta. In the worst case, each square contains 4 points, one at each corner. One of these points is Pi, leaving at most 7 points to be considered. This worst case situation is shown in the following figure. Notice that even though PL2 and PR1 have the same coordinates, they would be different points. For the actual analysis, it is only important that the number of points in the lambda by 2 lambda rectangle be big O of 1, and this much is certainly clear. Because at most 7 points are considered for each Pi, the time to compute a DC that is better than delta is big O of n. Thus, we appear to have an big O of n log n solution to the closest points problem based on the 2 half-sized recursive calls plus the linear extra work to combine the two results. However, we do not quite have an big O of n log n solution yet. The problem is that we have assumed D that a list of points sorted by y coordinate is available. If we perform this sort for each recursive call, then we have big O of n log n extra work. This gives an big O of n log square n algorithm. This is not all that bad, especially when compared to the brute force big O of n square. However, it is not hard to reduce the work for each recursive call to big O of n, thus ensuring an big O of n log n algorithm. We will maintain two lists. One is the point list sorted by x coordinate and the other is the point list sorted by y coordinate. We will call these lists P and Q respectively. These can be obtained by a pre-processing sorting step at cost big O of n log n and thus does not affect the time bound. PL and QL are the lists passed to the left half recursive call and PR and QR are the lists passed to the right half recursive call. We have already seen that P is easily split in the middle. Once the dividing line is known, we step through Q sequentially, placing each element in QL or QR as appropriate. It is easy to see that QL and QR will be automatically sorted by y coordinate. When the recursive calls return, we scan through the Q list and discard all the points whose x coordinates are not within the strip. Then Q contains only points in the strip, and these points are guaranteed to be sorted by their y coordinates. This strategy ensures that the entire algorithm is big O of n log n because only big O of n extra work is performed. Depth first search DFS. The strategy followed by depth first search is to search deeper in the graph whenever possible. Depth first search explores edges out of the most recently discovered vertex V that still has unexplored edges, leaving it. Once all of V's edges have been explored, the search backtracks to explore edges, leaving the vertex from which V was discovered. This process continues until we have discovered all the vertices that are reachable from the original source vertex. If any undiscovered vertices remain, then depth first search selects one of them as a new source and it repeats the search from that source. The algorithm repeats the entire process until it has discovered every vertex. As in breadth first search, whenever depth first search discovers a vertex v during a scan of the adjacency list of an already discovered vertex u, it records this event by setting v's predecessor attribute v.py to u. The predecessor subgraph produced by a depth first search may be composed of several trees because the search may repeat from multiple sources. Therefore, define the predecessor subgraph of a depth first search slightly differently from that of a breadth first search. Let g pi equals v, e pi, where e pi equals v dot pi, v, such that v belongs to capital V and v dot pi not equals nil. The predecessor subgraph of a depth first search forms a depth first forest comprising several depth first trees. The edges in e pi are tree edges. As in breadth first search, depth first search colors vertices during the search to indicate their state. Each vertex is initially blue, is greened when it is discovered in the search, and is blackened when it is finished, that is, when its adjacency list has been examined completely. This technique guarantees that each vertex ends up in exactly one depth first tree, so that these trees are disjoint. Besides creating a depth first forest, depth first search also timestamps each vertex. Each vertex v has two timestamps. The first timestamp v.t records when v is first discovered and greened, and the second timestamp v.f records when the search finishes examining v's adjacency list and blackens v. These timestamps provide important information about the structure of the graph and are generally helpful in reasoning about the behavior of depth first search. The procedure DFS below records when it discovers vertex u in the attribute u.d and when it finishes vertex u in the attribute u.f. These timestamps are integers between 1 and 2 mod v, since there is one discovery event and one finishing event for each of the modulus of v vertices. For every vertex u, u.d less than u.f. Vertex u is blue before time u.d, green between time u.d and u.f, and black thereafter. The following figure shows the pseudocode for the basic depth first search algorithm. The input graph G may be undirected or directed. The variable time is a global variable that used for timestamping. The procedure DFS works as follows. Lines 1, 2, 3 paint all vertices blue and initialize their pi attributes to nil. Line 4 resets the global time counter. Lines 5 to 7 check each vertex in V in turn, and when a blue vertex is found, visit it using DFS visit procedure. Every time DFS visit of G, U is called in line 7, vertex U becomes the root of a new tree in the depth first forest. When DFS returns, every vertex U has been assigned a discovery time U.D and a finishing time U.F. In each call, DFS visit of G, U, vertex U is initially blue. This figure shows the procedure DFS visit of G, U. The procedure DFS visit of G, U works as follows. Line 1 increments the global variable time. Line 2 records the new value of time as the discovery time U.D. Line 3 paints U green. Lines 4 to 7 examine each vertex V adjacent to U and recursively visit V if it is blue. As each vertex V belongs to adjacent U is considered in line 4, we say that edge U, V is explored by the depth first search. Finally, after every edge leaving U has been explored, lines 8 to 10 paint U in black, increment time and record the finishing time in U.F. Note that the results of depth first search may depend upon the order in which line 5 of DFS examines the vertices and upon the order in which line 4 of DFS visit visits the neighbors of a vertex. These different visitation orders tend not to cause problems in practice. Use any depth-first search result effectively with essentially equivalent results. What is the running time of DFS? The loops on lines 1 up to 3 and lines 5 up to 7 of DFS take time big theta of V exclusive of the time to execute the calls to DFS visit. As we did for breadth-first search, use aggregate analysis. The procedure DFS visit is called exactly once for each vertex V belongs to capital V. Since the vertex U on which DFS visit is invoked must be blue, and the first thing DFS visit does is paint vertex U green. During an execution of DFS visit of G, V, the loop on lines 4 to 7 executes mod adjacent of V times. Since summation of V belongs to capital V, modulus of adjacent V equals big theta of E. The total cost of executing lines 4 to 7 of DFS visit is big theta of E. The running time of DFS is therefore big theta of V plus E. Example, directed graph with 6 vertices and 8 edges is shown here. This figure illustrates the progress of DFS on the graph. Conduct a depth-first search on the graph starting with node U, and the discovery time of this node is 1. This node is shaded by green color to show this node is discovered. Consider nodes adjacent to U, then decide to visit V first. Rule: visit adjacent nodes in alphabetical order, and discovery time of this node is 2, and it's changed to green after visit. Next, we discovered Y, and we give discovery time is 3, then the node shaded in green color. The node Y has only one edge to X, so the discovered node is X. Discovery time is 4, and now looking X in green. Then X has an edge to visit V. The node V is already discovered, and there is no undiscovered nodes to visit. Then it backtracks to vertex X. Here, the node X gets a finish time of 5, so the node is blackened. Then we backtrack to vertex Y. Now the vertex Y, there is no undiscovered adjacent nodes to visit. It is dead end. It gets finish time of 6. Now looking vertex Y in black, then Y backtracks to vertex V. The node V also a dead end, and it gets a finish time of 7, then it looks black. Vertex U has a forward edge to vertex X. X is a descendant of U. Here X is already finished node. Then the source node gets a finish time of 8. Now the edge reached source node of this graph. Further, we can use cross edge to connect with another graph. Hint: dashed edges are indicating non-tree edges, that is forward F, back B, or cross C edges. Here, those non-tree edges are labeled as F and B. A subgraph is connected with this graph. Here, DFS starts with vertex W. It has discovery time of 9. Then, this vertex W has a cross edge C to connect with vertex Y. Vertex Y is already finished, so it backtracks to W, and vertex W decides to visit Z. Shaded edge connects with Z. Discovery time of Z is 10. The vertex Z backtracks to itself. It shows back edge with label B. The finish time of vertex Z is 11, and it looks blackened to indicate finished. Then the vertex Z backtracks to vertex W, and it will get finish time of 12. Now every vertex in given graph is blackened, which means finished the depth first tree of the given graph. Properties of depth first search. Depth first search yields valuable information about the structure of a graph. The basic property of depth first search is that the predecessor subgraph G pi does indeed form a forest of trees. Since the structure of the depth first trees exactly mirrors the structure of recursive calls of DFS visit. That is, U equals V dot pi if and only if DFS visit of G, V was called during a search of U's adjacency list. Additionally, vertex V is a descendant of vertex U in the depth first forest if and only if V is discovered during the time in which U is green. Another important property of depth first search is that discovery and finishing times have parenthesis structure. If we represent the discovery of vertex U with a left parenthesis and represent its finish by a right parenthesis, then the history of discoveries and finishings makes a well-formed expression in the sense that the parentheses are properly nested. Properties of depth-first search is shown in this figure. It shows the result of a depth-first search of a directed graph. Vertices are time-stamped and edge types are indicated as in progress of DFS figure, which is already shown. Intervals for the discovery time and finishing time of each vertex correspond to the parenthesization shown in below figure. Each rectangle spans the interval given by the discovery and finishing times of the corresponding vertex. Only 3 edges are shown. If 2 intervals overlap, then one is nested within the other. The vertex corresponding to the smaller interval is a descendant of the vertex corresponding to the larger. The graph of part A, redrawn with all tree and forward edges going down within a depth-first tree and all black edges going up from a descendant to an ancestor. Classification of edges. Another interesting property of depth-first search is that the search can be used to classify the edges of the input graph G equals V, E. The type of each edge can provide important information about a graph. For example, a directed graph is acyclic if and only if a depth-first search yields no back edges. Define 4 edge types in terms of the depth-first forest G pi produced by a depth-first search on G. Tree edges are edges in the depth-first forest G pi. Edge U, V is a tree edge if V was first discovered by exploring edge U, V. Back edges are those edges U, V connecting to a vertex U to an ancestor V in a depth-first tree. Consider self-loops, which may occur in directed graphs, to be back edges. Forward edges are those non-tree edges of U, V connecting a vertex U to a descendant V in a depth-first tree. Cross edges. Cross edges are all other edges. They can go between vertices in the same depth-first tree as long as one vertex is not an ancestor of the other, or they can go between vertices in different depth-first trees. In any given figure of DFS progress and properties of DFS, edge labels indicate edge types. The given figure of DFS properties shows that all tree and forward edges head downward in a depth-first tree and all back edges go up. We can redraw any graph in this manner. The DFS algorithm has enough information to classify some edges as it encounters them. The key idea is that when we first explore an edge of U, V, the color of vertex V tells us something about the edge. Blue indicates a tree edge. Green indicates a back edge. And black indicates a forward or cross edge. The first case is immediate from the specification of the algorithm. For the second case, observe that the green vertices always form a linear chain of descendants corresponding to the stack of active DFS visit invocations. The number of green vertices is one more than the depth in the depth-first forest of the vertex most recently discovered. Exploration always proceeds from the deepest green vertex, so an edge that reaches another green vertex has reached an ancestor. The third case handles the remaining possibility. In undirected graph U, V and V, U are really the same edge. In such a case, classify the edge as the first type in the classification list that applies. Equivalently, classify the edge according to whichever of U, V or V, U the search encounters first. Show that forward and cross edges never occur in a depth-first search of an undirected graph. Euler 2. Consider the following 3 figures. A popular puzzle is to reconstruct these 3 figures using a pen, drawing each line exactly once. The pen may not be lifted from the paper while the drawing is being performed. As an extra challenge, make the pen finish at the same point at which it started. This figure, the first figure of the above diagram, can be drawn only if the starting point is the lower left or right hand corner and it is not possible to finish at the starting point. The second figure is easily drawn with the finishing point the same as the starting point, but the third figure cannot be drawn at all within the parameters of the puzzle. We can convert this problem to a graph theory problem by assigning a vertex to each intersection. Then the edges can be assigned in the natural manner, as shown in this figure. After this conversion is performed, must find a path in the graph that visits every edge exactly once. If we are to solve the extra challenge, then we must find a cycle that visits every edge exactly once. Motivation and origin of Euler 2. The existence of closed trails containing all the edges in a graph is the subject of first paper in graph theory. It was written by Leonhard Euler, thus initiating the theory of graphs. Like many combinatorial problems, Euler's paper has its motivation in a problem that can be easily stated. Königsberg 7-bridge problem. The river Pigel flows through the city of Königsberg, located in Russia, dividing the city into 4 land regions, of which 2 are banks and 2 are islands. During the time of Euler, the 4 land regions were connected by 7 bridges, as shown in this figure. The citizens of Königsberg had an entertaining exercise. Start from any land region and come back to the starting point after crossing each of the 7 bridges exactly once. Euler explained that it is impossible to do so by using the terminology of points representing the land regions and lines representing the bridges. Hence, he titled his paper as Solutions to a Problem Relating to the Geometry of Positions. Through this explanation, he laid the foundation for graph theory. Definitions. A trail in a graph which contains all its edges is called an Eulerian trail. It can be open or closed. A graph is called an Eulerian graph if it contains a closed Eulerian trail. Note that an Eulerian graph is necessarily connected. Moreover, if G is Eulerian, then one can choose an Eulerian trail starting and ending from any given vertex. Theorem: Euler, a connected graph G is Eulerian if every vertex has even degree. Proof: G is Eulerian implies every vertex has even degree. Let W equals V0, E1, V1, E2, V2, and it goes up to Vt minus 1, Et, Vt is equals V0. Be a closed Eulerian trail in G. If Vi is an internal vertex not equals V0 of W appearing k times, then degree G of Vi equals to k. If V0 appears r times internally, then degree G of Vi equals 2r plus 2. Proof due to Fowler in 1988. Every vertex is of even degree implies G is Eulerian. This implication is proved by induction on M. If M less than or equals 2, then G is one of the following 4 graphs. Clearly, each of item is Eulerian. We proceed to prove the induction step, assuming that the implication holds for all connected graphs with at most m-1 edges and that G has m edges. Let X be any vertex of G and X, W1, X, W2 be 2 of the edges incident with X. W1 and W2 need not be distinct. This figure shows all connected graphs with at most 2 edges and every vertex of even degree. Consider the graph H obtained from G by deleting X, W1 and X, W2 and adding a new edge F equals W1, W2 as shown in below. Construction of a new graph and the extension of a trail is shown. The graph H has m-1 edges and its every vertex has even degree. However, H may be connected or disconnected. So, we consider two cases. Case 1. H is connected. By induction hypothesis, H contains a closed Eulerian trail. Say W equals V0, E1, it goes up to V0. Then the trail W equals V0, E1, it goes up to V0, is a closed trail in G. Case 2. H is disconnected. In this case, H contains two components, say C and D, such that X belongs to C and F belongs to D. Both the graphs C and D have less than M edges, and every vertex in V of C union V of D is even. Hence, by induction hypothesis, C and D contain Eulerian trails, say W1 of X, X and W2 equals V0, E1, V1, it goes up to V0. Then V0, E1, V1, it goes up to X, W2 or Z, it goes up to V0, an Eulerian trail in G. Using the above theorem, it is easy to conclude that the graph of Königsberg is non-Eulerian. Corollary: if a connected graph G contains exactly two vertices of odd degree, say X and Y, then it contains a X, Y Eulerian trail. Proof: let G star be a new graph obtained by adding a new vertex Z and joining it to X and Y. Clearly, G star is an Eulerian graph in which Z has degree 2. Without loss of generality, let W equals Z, X, X, it goes up to Y, Z, Z. Be a closed Eulerian trail in G star, but then the subtrail W dash equals X, it goes up to Y of W is a required XY trail in G. Corollary: if a connected graph G contains 2k greater than or equals to vertices of odd degree, then E of G can be partitioned into k sets E1, E2 goes up to Ek, such that each EI induces a trail. Proof: apply the above proof technique. Fleury's algorithm to generate a closed Eulerian trail. Though Euler's theorem neatly characterizes Eulerian graphs, its proof is existential in nature. Fleury, in 1983, described an algorithm to generate a closed Eulerian trail in a given connected graph in which every vertex has even degree. In the following, we describe this algorithm and prove that it indeed generates an Eulerian trail. Fleury's algorithm. Input: a weighted connected graph G, W in which every vertex has even degree. Output: a closed Eulerian trail W. Step 1. Choose a vertex V0 arbitrarily and define the trail W0 equals V0. Step 2. After selecting a trail, say Wk equals V0, E1, V1, it goes up to Vk-1, Ek, Vk. Form the graph Gk equals Gk-1 minus Ek, that is Gk equals G minus within set E1, E2, it goes up to Ek, where G0 equals G. Step 3. If there is no edge incident with Vk in Gk, then stop. Declare Wk is a closed Eulerian trail of G. If there is an edge incident with Vk in Gk, select an edge, say Ek plus 1 equals Vk, Vk plus 1, giving preference to a non-cut edge of Gk. Define Wk plus 1 equals V0, E1, it goes up to Ek plus 1, Vk plus 1. Go to step 2 with Wk plus 1. An illustration: the trails W1, it goes up to W10, and the graphs G1 up to G10, generated by the algorithm are shown below. W10 is a closed Eulerian trail. For simplicity, we have shown the trails with edges alone. Below figures shows the iterations of Fleury's algorithm. Input graph with W equals V0 and G equals G0 is shown. In this figure, W1 equals V0, V2 and G1 equals G minus E of W1, that is edges of W1. W2 equals V0, V2 and V2, V1. Then G2 equals G minus E of W2. W3 equals V0, V2, V2, V1 and V1, V3. Then G3 equals G minus E of W3. W4 equals W3 implies V3, V5. Then G4 equals G minus E of W4. W5 equals W4 implies V5, V4. Then G5 equals G minus E of W5. W6 equals W5 implies V4, V2. And G6 equals G minus E of W6. W7 equals W6 implies V2, V3. G7 equals G minus E of W7. W8 equals W7 implies V3, V4. And G8 equals G minus E of W8. W9 equals W8 implies V, V4, V1. And G9 equals G minus E of W9. W10 equals W9 implies V1, V0 and G10 equals G minus E of W10. Look at the graph G2 of the above figure. There are 3 edges incident with V1. To proceed further, we cannot select the edge V1, V0. See step 3.2. We can select V1, V3 or V1, V4. We have decided to select V1, V3 arbitrarily. Theorem. Correctness of the algorithm. Every trail constructed by Fleury's algorithm is a closed Eulerian trail. Proof. Let WP equals V0, E1, it goes up to EP, VP, be a trail generated by the algorithm. Claim 1. WP is a closed trail. That WP is a trail is obvious by step 2, since in every iteration we select an edge which has not been selected in the earlier iterations. Moreover, by step 3.2, there are no more edges incident with VP. Therefore, if V0 not equals VP, then degree G of VP equals 2k plus 1, where k is the number of items VP appears internally in WP, which is a contradiction. Hence, we conclude that V0 equals VP. Claim 2. WP contains all the edges of G. Assume the contrary and let GP equals G minus E of WP. So, E of GP not equals null. Hence, there are vertices of positive degree in GP. Moreover, every vertex in GP has even degree, since GP is obtained from G by deleting the edges of a closed trail. Let S equals V belongs to capital V of GP such that degree GP of V greater than 0. Let H equals S. Then VP belongs to V minus S. Since degree GP of VP equals 0 by step 3.1. A step in the proof of theorem, correctness of algorithm, is shown. Let Vk be the last vertex in WP such that Vk belongs to S. Then Vk plus 1 belongs to V minus S and Ek plus 1 equals Vk, Vk plus 1 is the only edge joining S and V minus S in GP. Therefore, we conclude that Ek plus 1 is a cut edge of GP. Next, since every vertex of H has positive degree, there exists an edge E incident with Vk in H. It is not a cut edge of H since every vertex in H has even degree. E is not a cut edge of GP2 since H is a subset of GP. While executing the k plus 1th iteration, we have preferred to select ek plus 1 rather than e. Hence, 2. Ek plus 1 is not a cut edge of GP by Furey's rule step 3.2. The conclusions 1 and 2 contradict each other. Hence, claim 2 holds and WP is a closed Eulerian trail. Generic minimum spanning tree. Electronic circuit designs often need to make the pins of several components electrically equivalent by wiring them together. To interconnect a set of n pins, we can use an arrangement of n1 wires, each connecting 2 pins. Of all such arrangements, the one that uses the least amount of wire is usually the most desirable. We can model this wiring problem with a connected, undirected graph G equals V, E, where V is these 2 F pins, E is the set of possible interconnections between pairs of pins, and for each edge U, V belongs to capital E, we have a weight W of U, V, specifying the cost, amount of wire needed to connect U and V. Then wish to find an acyclic subset T, E that connects all of the vertices and whose total weight is minimized. W of T equals summation of U, V belongs to T, W of U, V. Since T is a cyclic and connects all of the vertices, it must form a tree, which we call a spanning tree since it spans the graph G. Call the problem of determining the tree T the minimum spanning tree problem. The below figure shows an example of a minimum spanning tree for a connected graph. The weights on edges are shown and the edges in a minimum spanning tree are shaded. The total weight of the tree shown is 37. This minimum spanning tree is not unique. Removing the edge B, C and replacing it with the edge A, H yields another spanning tree with weight 37. Examine 2 algorithms for solving the minimum spanning tree problem, Kruskal's algorithm and Prim's algorithm. Easily make each of them run in time big O of E log V using ordinary binary heaps. By using Fibonacci heaps, Prim's algorithm runs in time big O of E plus V log V, which improves over the binary heap implementation if mod V is smaller than mod E. Each step of a greedy algorithm must make one of several possible choices. The greedy strategy advocates making the choice that is the best at the moment. Such a strategy does not generally guarantee that it will always find globally optimal solutions to problems. For the minimum spanning tree problem, prove that certain greedy strategies yield a spanning tree with minimum weight. Generic minimum spanning tree method that grows a spanning tree by adding one edge at a time. Growing a minimum spanning tree. Assume that we have a connected undirected graph G equals V, E with a weight function W, E implies R, and find a minimum spanning tree for G. The two algorithms, Kruskal's and Prim's algorithms, use a greedy approach to the problem, although they differ in how they apply this approach. This greedy strategy is captured by the following generic method, which grows the minimum spanning tree one edge at a time. The generic method manages a set of edges A, maintaining the following loop invariant. Prior to each iteration, A is a subset of some minimum spanning tree. At each step, determine an edge U, V that can add to A without violating this invariant. That is, that A union U, V is also a subset of minimum spanning tree, such an edge is safe edge for A. Since we can add it safely to A while maintaining the invariant. The following figure shows pseudocode for the generic MST. Use the loop invariant as follows. Initialization. After line 1, the set A trivially satisfies the loop invariant. Maintenance. The loop in lines 2 to 4 maintains the invariant by adding only safe edges. Termination. All edges added to A are in a minimum spanning tree, and so the set A returned in line 5 must be a minimum spanning tree. Finding a safe edge in line 3, one must exist. Since when line 3 is executed, the invariant dictates that there is a spanning tree T such that A is a subset of T. Within the while loop body, A must be a proper subset of T. And therefore, there must be an edge u, v belongs to T such that u, v not belongs to A, and u, v is safe for A. A cut S, v minus S of an undirected graph G equals v, E is a partition of V. The below figure illustrates this notion. Two ways of viewing a cut S, v minus S of the graph from the given graph, which is shown above. Figure A is shown here. Black vertices are in the set S and blue vertices are in the set V minus S. The edges crossing the cut are those connecting white vertices with black vertices. The edge D, C is the unique light edge crossing the cut. A subset A of the edges is shaded. Note that the cut S, V minus S respects A since no edge of A crosses the cut. Figure B, shown here. The same graph with the vertices in the set S on the left and the vertices in the set V minus S on the right. An edge crosses the cut if it connects a vertex on the left with a vertex on the right. An edge u, v belongs to E crosses the cut S, V minus S if one of its endpoints is in S and the other is in V minus S. A cut respects a set A of edges if no edge in A crosses the cut. An edge is a light edge crossing a cut if its weight is the minimum of any edge crossing the cut. Note that there can be more than one light edge crossing a cut in the case of ties. Rule for recognizing safe edges is given by the following theorem. Theorem: let G equals V, E be a connected, undirected graph with a real valued weight function W defined on E. Let A be a subset of E that is included in some minimum spanning tree for G. Let S, V minus S be any cut of G that respects A, and let u, v be a light edge crossing S, V minus S. Then edge u, v is safe for A. Proof: let T be a minimum spanning tree that includes A and assume that T does not contain the light edge u, v. Construct another minimum spanning tree T dash that includes A union u, v by using a cut and paste technique, thereby showing that u, v is a safe edge for A. The edge u, v forms a cycle with the edges on the simple path P from U to V in T, as shown in this figure. Since U and V are on opposite sides of the cut S, V minus S, at least one edge in T lies on the simple path P and also crosses the cut. Let X, Y be any such edge. The edge X, Y is not in A because the cut respects A. Since X, Y is on the unique simple path from U to V in T, removing X, Y breaks T into two components. Adding U, V reconnects them to form a new spanning tree T dash equals T minus X, Y union U, V. T dash is a minimum spanning tree since U, V is a light edge crossing S, V minus S and X, Y also crosses this cut W of U, V less than or equal to W of X, Y. Therefore, W of T dash equals W of T minus W of X, Y plus W of U, V, which is less than or equals W of T. But T is a minimum spanning tree so that W of T less than or equals W of T dash. Thus, T dash must be a minimum spanning tree also. It remains to show that U, V is actually a safe edge for A. A is a subset of T dash since A is a subset of T and X, Y does not belongs to A. Thus, A union U, V is a subset of T dash. Consequently, since T dash is the minimum spanning tree, U, V is safe for A. The above theorem gives us a better understanding of the workings of the generic MST method on a connected graph G equals V, E. As the method proceeds, the set A is always acyclic. Otherwise, a minimum spanning tree including A would contain a cycle, which is a contradiction. At any point in the execution, the graph GA equals V, A is a forest, and each of the connected components of GA is a tree. Any safe edge U, V for A connects distinct components of GA, since A union U, V must be acyclic. The while loop in lines 2 to 4 of generic MST executes modulus of Vj times because it finds one of the modulus of V minus 1 edges of a minimum spanning tree in each iteration. Initially, when A equals null, there are modulus of V trees in GA, and each iteration reduces that number by 1. When the forest contains only a single tree, the method terminates. The Kruskal's and Prime's algorithms follows the following corollary. Corollary: let G equals V, E be a connected, undirected graph with a real valued weight function, W, defined on E. Let A be a subset of E that is included in some minimum spanning tree for G, and let C equals VC, EC be a connected component tree in the forest GA equals V, A. If U, V is a light edge connecting C to some other component in GA, then U, V is safe for A. Proof: the cut C of VC, V minus VC respects A, and U, V is a light edge for this cut. Therefore, U, V is a safe for A. Incremental design or union find structure. We can view some graph algorithms such as a process that starts with a forest of singleton vertices and gradually connects the graph by adding edges and growing the trees. The algorithm connects distinct trees, connected components, and edge whose endpoints are within the same tree may not be added since it induces cycles. Therefore, we can maintain a data structure that supports the following operations. Find operation. For a vertex, find out which connected component it belongs to. Union operation. Combine two connected components. For obvious reasons, such a data structure is called a union find structure and can be seen in a more general context where we have a family of subsets and for any given element. We can find the subset it belongs to and we can merge two subsets into one. The subsets are assumed to be disjoint. Simple data structure for union find. Let us try to use arrays to represent the sets. Viz. In an array A, let A of I contains the label of vertex I. The labels are also in the range 1, 2. It goes up to n. Initially, all the labels are distinct. For each set label, we also have pointers to all its elements. That is, the indices of the array that belong to the set. Find. It really simple for vertex I, report A of I. This takes big O of 1 time. Union. To do union Sj, Sk, we change the label of all elements pointed to by j and link them with k. Thus, after union, we have labeled all the elements in the union as k. The time for this operation is proportional to the number of elements in set J. For obvious reasons, we would change labels of the smaller subsets. Foster scheme. We want to design better schemes for graphs with fewer edges. For this, we will explore Foster schemes for union find. Instead of arrays, let us use trees to represent subsets. Initially, all trees are singleton nodes. The root of each tree is associated with a label of the subset and a rank which denotes the maximum depth of any leaf node. To perform find of x, we traverse the tree starting from the node x till we reach the root and report its label. So the cost of a find operation is the maximum depth of a node. To perform union of t1, t2, we make the root of one tree the child of the root of the other tree. To minimize the depth of a tree, we attach the root of the smaller rank tree to the root of the larger rank tree. This strategy is known as the union by rank heuristic. The rank of a tree increases by 1 only when T1 and T2 have the same ranks. Once a root node becomes a child of another node, the rank doesn't change by convention. The union operation takes big O of 1 steps. Path compression. When we do a find of x operation, let x naught equals root of x, x1, x2, it goes up to x, be the sequence of nodes visited. Then we make the subtrees rooted at xi minus the subtree rooted at xi plus 1, the children of the root node. Clearly, the motivation is to bring more nodes closer to the root node, so that the time for the find operation decreases. And path compression does not increase the asymptotic cost of the current find operation, it's factor of 2. Integrated things together. The cost of find holds key to the analysis of this union find data structure. Since the rank is less than log n, we already have an upper bound of log n for any individual find operation. We will adopt the following strategy for counting the cost of find operations. We will associate a hypothetical counter with each node that we will increment whenever it's visited by some find operation. Finally, by summing the counts of all the nodes, we can bound the cost of all the find operations. We will refer to the incremental cost of find operation as a charge. Two types of charges: block charge, path charge. Block charge. If the block number of the parent node P of V is strictly greater than a node V, that is B inverse rank of P of V greater than B inverse of rank of V, then we assign a block charge. Path charge. Any charge incurred by a find operation that is not a block charge. From our previous observation, we will focus on counting the path charges. Matching. Graph matching is an algorithm to solve matching problems on graphs. A simple example of a matching problem occurs when we have a set of teachers to assign to a set of courses. Each teacher is qualified to teach certain courses but not others. We wish to assign a course to a qualified teacher so that no two teachers are assigned the same course. With certain distributions of teachers and courses, it is impossible to assign every teacher a course. In those situations, we wish to assign as many teachers as possible. We can represent this situation by a graph as in below, where the vertices are divided into two sets V1 and V2, such that vertices in the set V1 represent teachers and vertices in the set V2 represent courses. That teacher V is qualified to teach course W is represented by an edge V, W. A graph such as this, whose vertices can be divided into two disjoint groups with each edge having one end in each group, is called bipartite. Assigning a teacher a course is equivalent to selecting an edge between a teacher vertex and a course vertex. The matching problem can be formulated in general terms as follows. Given a graph G equals V, E, a subset of the edges in E with no two edges incident upon the same vertex in V is called a matching. The task of selecting a maximum subset of such edges is called the maximal matching problem. The heavy edges are an example of one maximal matching in that graph. A complete matching is the matching in which every vertex is an endpoint of some edge in the matching. Clearly, every complete matching is a maximal matching. There is a straightforward way to find maximal matchings. We can systematically generate all matchings and then pick one that has the largest number of edges. The difficulty with this method is that it has a running time that is an exponential function of the number of edges. There are more efficient algorithms for finding maximal matchings. These algorithms generally use a technique known as augmenting paths. Let M be a matching in a graph G. A vertex V is matched if it is the endpoint of an edge in M. A path connecting two unmatched vertices in which alternate edges in the path are in M is called an augmenting path relative to M. Observe that an augmenting path must be of odd length and must begin and end with edges not in M. Also observe that given an augmenting path P, we can always find a bigger matching by removing from M those edges that are in P and then adding to M the edges of P that were initially not in M. The new matching is M circle plus P, where circle plus denotes exclusive or on sets. That is, the new matching consists of those edges that are in M or P, but not in both. The below figure shows a graph and a matching M consisting of the heavy edges 1, 6, 3, 7 and 4, 8. The path 2, 6, 1, 8, 4 and 9 in below figure is an augmenting path relative to M. The below figure shows the matching 1, 8, 2, 6, 3, 7 and 4, 9 obtained by removing from M those edges that are in the path and then adding to M the other edges in the path. The key observation is that M is a maximal matching if and only if there is no augmenting path relative to M. This observation is the basis of our maximal matching algorithm. M circle plus N contains an augmenting path relative to M. Consider the graph G dash equals V, M circle plus N. Since M and N are both matchings, each vertex of V is an endpoint of at most one edge from M and an endpoint of at most one edge from N. Thus, each connected component of G dash forms a simple path, possibly a cycle, with the edges alternating between M and N. Each path that is not a cycle is either an augmenting path relative to M or an augmenting path relative to N, depending on whether it has more edges from N or from M. Each cycle has an equal number of edges from M and N. Procedure to find a maximal matching M for a graph G equals V, E. Start with M equals null. Find an augmenting path P relative to M and replace M by M circle plus P. Repeat step 2 until no further augmenting paths exist, at which point M is a maximal matching. It remains only to show how to find an augmenting path relative to a matching M. Do this for the simpler case where G is a bipartite graph with vertices partitioned into sets V1 and V2. Build an augmenting path graph for G for levels I equals 0, 1, 2 and so on using a process similar to breadth first search. Level 0 consists of all unmatched vertices from V1. At odd level I, add new vertices that are adjacent to a vertex at level I-1 by a non-matching edge, and we also add that edge. At even level I, add new vertices that are adjacent to a vertex at level I-1 because of an edge in the matching M together with that edge. Continue building the augmenting path graph level by level until an unmatched vertex is added at an odd level or until no more vertices can be added. If there is an augmenting path relative to M, an unmatched vertex V will eventually be added at an odd level. The path from V to any vertex at level 0 is an augmenting path relative to M. Example. The below figure illustrates the augmenting path for the graph part A in the figure of matching, relative to the matching in figure of large matching, in which we have chosen vertex 5 as the unmatched vertex at level 0. At level 1, we add the non-matching edge 5, 6. At level 2, we add the matching edge 6, 2. At level 3, we can add either of the non-matching edges 2, 9 or 2, 10. Since both vertices 9 and 10 are currently unmatched, we can terminate the construction of the augmenting path graph after the addition of either one of these vertices. Both paths 9, 2, 6, 5 and 10, 2, 6, 5 are augmenting paths relative to the matching in the figure of larger matching. Suppose G has n vertices and e edges. Constructing the augmenting path graphs for a given matching takes big O of e time if we use an adjacency list representation for edges. Thus, to find each new augmenting path takes big O of e time. To find a maximal matching, we construct at most n by 2 augmenting paths. Since each enlarges the current matching by at least one edge, therefore, a maximal matching may be found in big O of n time for a bipartite graph G. Strongly connected components. A directed graph is strongly connected if there exists a path from U to V and also a path from V to U for every distinct pair of nodes U and V. If a directed graph is not strongly connected or interested in the largest sets of nodes such that the corresponding subgraphs are strongly connected, each of these subgraphs is called a strongly connected component of the original graph. In this graph, which is shown in this figure, for instance, nodes 1, 2 and 3 and the corresponding edges from a strongly connected component. Another component corresponds to the nodes 4, 7 and 8. Despite the fact that there exist edges 1, 4 and 1, 8, it is not possible to merge these two strongly connected components into a single component because there exists no path from node 4 to node 1. This figure shows to the left of each node the number thus assigned. The following algorithm finds the strongly connected components of a directed graph G. Carry out a depth-first search of the graph starting from an arbitrary node. For each node V of the graph, let postnum of V be the number assigned during the search. Construct a new graph G'. G' is the same as G, except that the direction of every edge is reversed. Carry out a depth-first search in G'. Begin this search at the node W that has the highest value of postnum. If G contains n nodes, it follows that postnum of W equals n. If the search starting at W does not reach all the nodes, choose as the second starting point the node that has the highest value of postnum among all the unvisited nodes and so on. To each tree in the resulting forest, there corresponds one strongly connected component of G. The graph G' is illustrated in this figure, with the values of postnum shown to the left of each node. Carry out a depth-first search starting from node 5 since postnum of 5 equals 8. The search reaches nodes 5 and 6. For a second starting point, choose node 1 with postnum of 1 equals 6. This time the search reaches nodes 1, 3 and 2. For the third starting point, take node 4 with postnum of 4 equals 5. This time the remaining nodes 4, 7 and 8 are all reached. The corresponding forest is illustrated in this figure. The strongly connected components of the original graph are the subgraphs corresponding to the set of nodes 5, 6, 1, 3, 2, and 4, 7, 8. It is harder to prove the result the other way. Let V be a node, that is, in the tree whose root is R, when we carry out the search of G dash and suppose V not equals R. This implies that there exists a path from R to V in G dash. Thus there exists a path from V to R in G. When carrying out the search of G dash, always choose as a new starting point, that is, as the root of a new tree, that node not yet visited with the highest value of post num. Since we chose R rather than V to be the root of the tree in question, have post num of R greater than post num of V. When we carried out the search in G, three possibilities seemed to be open a priori. R was an ancestor of V. R was a descendant of V. Or R was neither an ancestor nor a descendant of V. The second possibility is ruled out by the fact that post num of R greater than post num of V. In the third case, it would be necessary for the same reason that R be to the right of V. However, there exists at least one path from V to R in G. Since in a depth-first search, the edges not used by the search never go from left to right. Any such path must go up the tree from V to a common ancestor, X, say, of V and R, and then go down the tree to R. But this is quite impossible. We should have post num of X greater than post num of R, since X is an ancestor of R. Next, since there exists a path from V to X in G, there would exist a path from X to V in G dash. Before choosing R as the root of the tree in search of G dash, we would have already visited X. Otherwise, X rather than R would be chosen as the root of the new tree, and therefore also V. This contradicts the hypothesis that V is in the tree whose root is R when we carry out the search of G. Only the first possibility remains: R was an ancestor of V when we searched G. This implies that there exists a path from R to V in G. Thus proved that if node V is in the tree whose root is R when we carry out the search of G dash, then there exists in the G both a path from V to R and a path from R to V. If two nodes U and V are in the same tree when we search G dash, they are therefore both in the same strongly connected component of G, since there exist paths from U to V and from V to U in G via node R. Topological sort. A topological sort is an ordering of vertices in a directed acyclic graph, DAG, such that if there is a path from Vi to Vj, then Vj appears after Vi in the ordering. Use depth-first search to perform a topological sort of a directed acyclic graph. A topological sort of a DAG, G has V, E in a linear ordering of all its vertices, such that if G contains an edge U, V, then U appears before V in the ordering. It is clear that a topological ordering is not possible if the graph has a cycle, since for two vertices V and W on the cycle, V precedes W and W precedes V. Furthermore, the ordering is not necessarily unique. Any legal ordering will do. In the graph, which is shown in this figure, V1, V2, V5, V4, V3, V7, V6 and V1, V2, V5, V4, V7, V3 and V6 are both topological ordering. View a topological sort of a graph as an ordering of its vertices along a horizontal line so that all directed edges go from left to right. Many applications use directed acyclic graph to indicate precedences among events. A simple algorithm to find a topological ordering is first to find any vertex with no incoming edges. Then print this vertex and remove it along with its edges from the graph. Then apply this same strategy to the rest of the graph. To formalize this, define the in degree of a vertex v as the number of edges u, v. Compute the in degrees of all vertices in the graph, assuming that the in degree for each vertex is sorted and that the graph is read into an adjacency list. Apply the algorithm which is shown in this figure to generate a topological ordering. The function find new vertex in degree 0 scans the array of vertices looking for a vertex with in degree 0 that has not already been assigned a topological number. It returns not a vertex if no such vertex exists. This indicates that the graph has a cycle. Because find new vertex of in degree 0 is a simple sequential scan of the array of vertices. Each call to it takes big O of modulus of v time. Since there are modulus of v such calls, the running time of the algorithm is big O of mod v square. By paying more careful attention to the data structures, it is possible to do better. The cause of the poor running time is the sequential scan through the array of vertices. If the graph is sparse, expect that only a few vertices have their in degrees updated during each iteration. However, in the search for a vertex of in degree 0, look at potentially all the vertices even though only a few have changed. Remove this inefficiency by keeping all the unassigned vertices of in degree 0 in a special box. The find new vertex of in degree 0 function then returns and removes any vertex in the box. When we decrement the in degrees of the adjacent vertices, check each vertex and place it in the box if its in degree falls to 0. To implement the box, use either a stack or a queue. We will use a queue. First, the in degree is computed for every vertex. Then all vertices of in degree 0 are placed on an initially empty queue. While the queue is not empty, a vertex v is removed. All vertices adjacent to v have their in degrees decremented. A vertex is put on the queue as soon as its in degree falls to 0. The topological ordering then is the order in which the vertices dequeue. This figure shows the status after each phase in the given graph. Let us assume that the graph is already read into an adjacency list and that the in degrees are computed and stored with the vertices. Also assume each vertex has a named data member, top num, in which to place its topological numbering. The time to perform this algorithm is big O of mod e plus mod v if adjacency lists are used. This is apparent when one realizes that the body of the for loop is executed at most once per edge. Computing the in degrees can be done with the following code. This same logic shows that the cost of this computation is big O of mod e plus mod v, even though there are nested loops which is shown in this figure. The queue operations are done at most once per vertex and the other initialization steps, including the computation of in degrees, also take time proportional to the size of the graph. Conclusion. In this chapter, we have covered the following in detail. Breadth first search, BFS. Depth first search, DFS. Branch and bound. Topological sort. Strongly connected components. Euler 2. Generic minimum spanning tree. Bellman-Ford algorithm. Matching. Incremental design. And closest pair problem.